Hi guys, look, very privileged to be here with you. I'm going to talk about some of the work that we've been doing to address what we think is a really important challenge in integrating the technologies as the sort of associated with automation of mining, but I guess more generally just mining technology, and where that fits into a sort of long-term sustainable framework. In terms of where mining's going, I guess this is almost an iconic type of picture now. We sort of imagine the new face of mining being a world in which information is very rich and flows through screens, and there are centres of control, often remote from the operations, and leading to sort of images of this type which pervade. Yet this picture isn't from a mining operation, it's actually from the war room of a USS cruiser. It was the USS Valley Forge. It was commissioned in 1987. It was expected to have a 40-year service life, $1 billion asset. It was fitted with the Aegis I weapon or warfare system, the same technology that the Australian Navy has chosen for its systems. And as a rather cautionary tale, I think, to mining, when they look to upgrade this technology on board the ship and move to the second generation Aegis system, they found the cost of doing so exceeded the value of the asset and chose, instead of upgrading, to sink the ship off the coast of Hawaii. And this is, I think, a cautionary tale for us, because in a lot of ways where we're going with the technologies that are emerging in mining around automation and other areas are possibly leading us down the same pathway, where we find ourselves stovepiped by what we've done in the past and unable to move forward into to new things. Where do we come from? Where do these views come from? Well, as in the introduction, it was noted that one of the roles that I serve is as the program leader for our automation program within the Centre for Mining, Cooperative Research Centre for Mining. This is a Commonwealth government-funded centre, or combined Commonwealth and industry-funded centre, and it involves 4 universities here in WA: the University of Western Australia and Curtin University, and on the east coast the University of Queensland, where I'm based and where the centre is headed, and Newcastle University. And we have among our members most of the world's major mining companies and several of the large equipment manufacturers, including Caterpillar, P&H Sandvik, and some others. And the centre's been around for around about 22 years now. It was the very first centre funded under the Commonwealth Cooperative Research Centre scheme. It has its fingerprints over many of the technological developments that have occurred in mining over the many years. Just as a bit of a profile of some of our current technologies, I will talk first to this one. This is a technology that we've been involved with P&H. P&H are a manufacturer of what are known as electric mining shovels, large mining excavators. They're the workforce of hard rock mining in most parts of the world, perhaps WA's accepted there, and their very significant involvement in coal and other areas as well. And one of the key risks that occurs around these machines is the possibility that as they load trucks, they're able to collide with them, and the large amount of energy involved in moving 100 tonnes of dirt, 90 tonnes of bucket, and several thousand tonnes of machine house around can cause significant damage. And so this is a technology which provides a layer of protection around the truck, and you can see here in this video that as the operator tries to drive into the truck, he is inhibited for doing so. And this is just as an example. Here is another example based on the same equipment, but now looking at automating the swing loading cycle of the machine. Here the operator is still performing the dig, but he passes over to an automation system which plans a trajectory that takes the bucket up over the truck, works out where the truck is to a precision that sees no point of that truck more than 200 centimetres from where the system believes it to be, establishes what the current load distribution in the truck is based on various scanning technologies, and decides to place its load to equalise that distribution and so forth. These are technologies. The first is one which probably within the next 2 years will be a commercial product, and this one is 5 years out. Other companies that we've been involved with in technology development, I just need to do this. Bear with me. Okay. A significant risk occurs around operation of bulldozers on stockpiles and in other applications where, particularly if the material is drawn from under those stockpiles, there's the possibility of material bridging. The dozer operator is not aware of that, and he can drive over a bridge, collapse into a void, and face the risk of engulfment. And there, of course, have been many deaths over the past 10 years, several in Queensland where this has occurred. The idea of remotely controlling bulldozers is, of course, not new, and there are several companies, including Caterpillar, who we worked with in this particular project, who have developed technologies. And you can really think of them in sort of two phases. There's systems or technology where the remote operator, has direct line of sight of the machine, and these technologies work quite well, but it's quite onerous on the operator, and a bit of a push to move the guy away from that direct line of sight. So he's sort of removed from the situation. His context is altered, and where he might, with direct line of sight, be able to achieve 80% of what he could on board, taken off board away from the machine, his performance drops quite dramatically down to often a fraction of what he might achieve. And so in this particular work we've been involved in looking at the provision of additional feedback to the operator, in particular providing him with motion, using sensing on board the dozer and replicating that back at the operator station so that he feels the rock and roll of the machine, with frequencies up to about 30 hertz, providing high quality visual feedback, so in various forms, 2D and in 3D, and high quality audio feedback. And a useful and interesting observation out of all of this work is we can now approach around about 90% of on-board performance when these technologies are there. So there are examples really just to set the scene for and give a little bit of context. But the real topic I want to talk about is a project that our membership, so mining companies and equipment manufacturers, became quite passionate about around 2 years ago, and it's taken us a little bit of time to get this one off the ground, because while there was a lot of passion, there wasn't a lot of definition in what was to be done. And this is the concept of a mining automation reference architecture that we've been working on. And if we look to characterise the mining automation landscape, see where it is, while there are some very exciting developments and some genuine movements forward in this area, by and large, the technology of mining automation is still quite immature, and it's in its early stages. It's spread across quite diverse equipment fleets potentially, and we have this situation where it would be possible to conceive of solutions in many instances, but they are highly challenged by the fact that the mining operations themselves seek to gain competitive advantage in the way they mine. And this in turn leads to them choosing or wanting to choose with great care the equipment they use and the way in which they use that. So this is a mix and match situation. We have a situation where the technology involved is being developed by many people in many different locations around the world, using many different technologies and doing it at different times. And there's this sort of sanguine hope that all of these things can come together and work together, work at the sort of at the pointy end, and that's a huge challenge. And of course, we all know that there's always disruptive technologies on the horizon which have the potential to rapidly change the way people think about solving problems, and along with just the general incremental improvements in technology that occur, we've got this constantly changing landscape. So our project was motivated. It had some practical context, but it was strongly motivated by the need for a common plan for bringing disparate technologies together to perform a mine-wide automation type solution. What would be involved in this? And I said the project had a start around 2 years ago. It took us probably the first year to work out where we were going with this and what we were trying to do. And so the work I'm going to report on now is one dimension of the project. There are some other dimensions that I don't have time to touch on, but we are continuing to work on it. And it has support from a number of important players here. We have, in broad terms, mining companies, OEMs and integration providers. So by those integration providers, I'm talking about companies like CSC. And the way we've been running this project, and we're always happy to have more involved because it's an important area, and I hope to convey that to you, is just by running some facilitation workshops and getting people to talk about their challenges and trying to sift through the ideas, usually around focus topics, and take that a little bit further. So when we talk about a reference architecture, what do we mean? And this is really important. We're not talking about the development of a standard or a set of standards, although existing standards and possible future standards may feed into this and have a place within the architecture. We're not talking about a way to solve or deliver solutions. We're talking about a set of concepts that allow us to pose or at least establish a context in which innovation can occur with a minimum number of impediments to it. And this, of course, challenges many involved in their own agendas. But if we are to see long and sustained innovation in mining technology, and that is fundamentally important to the ability to reduce costs, this is something that we must do. Set up for ways in which we can allow people to innovate and not be prescriptive about the way they solve problems, but give guidance on how they should engineer solutions to fit into a broader whole. And there are many different stakeholders involved here. We've got 4 groups that I'll talk about, and they all come from very different points of view. The mining companies, of course, are looking for technology they can use to reduce their costs and use it in ways which they might consider to be their own intellectual property. The OEMs want to make one product and do not want to customise that product to fit within a particular mining company's view of the world, because that influences their whole quality control process and costs that go with it. We have systems integrators that are looking for reusable frameworks that are aligned to their end user needs, so that they are able to engineer systems in a reliable way without having to reinvent the wheel all the time. And technology providers, and between Queensland and WA, there's an enormous industry associated with the provision of technology, and many of the people at this show are involved in that, which are a significant part of our economy. They need, or they would benefit from, having accepted structures that they could work within, so that they're able to provide their, if you like, a long-term sustainable product line without having to re-engineer, when somebody moves from being a modular site to a MineStar site, or things like that that inevitably occur. So that describes our stakeholders. Of course, there are many challenges around this, and we've looked in the work we've done to date in putting some controls around the challenges, so that at least we're able to find a scope that is addressable. And among those challenges is a key issue of finding the right level of detail at which to work. So I'm going to give some examples of the areas or the level of detail at which we've been thinking about this. Many will say, oh, that's far too coarse-grained, and others will tell me it's far too fine-grained, depending on their own perspectives. But we've worked hard to find a methodology. But we have, in doing the work, tried to act as facilitators and collaborators of stakeholder, or collators of stakeholder views and perspectives, capturing what different people think and where they're trying to come from. And we've tried to keep it very grounded in examples that people are able to think about themselves at various levels of detail. We've also tried to avoid being prescriptive in the way when we've come to look at solutions. We've tried to offer as many different pathways to solutions to the generic problems that arise as we can, in order that nobody is disadvantaged in the way they currently would propose technology, but equally as we go forward there aren't ties that bind people to doing things certain ways, and this in turn, as we get a better view or understanding of the problem, changes and shapes our thinking. So our methodology, as I said, we've worked with concrete examples that we try to use to identify architectural requirements associated with automation use cases. So it's very much a case of going from the particular and hoping to find the general elements. We have looked, because there is an enormous amount of work involved in sifting and sorting through these and getting strong stakeholder engagement, we have looked to develop a set of architectural requirements from a partial set, and I'll talk about the 3 representative use cases that we've employed here. And perhaps the most important of all is the need for a language, a common language that people can use in talking to each other about this area, because I'm sure many of you will have had the experience when an IT guy meets a mining guy, they really have nothing to say to each other because their languages are so different that they're unable to really communicate in any significant way the depth of the ideas that are behind some of the words they use. And so we've tried to find a common reference language that is able to address that issue and try to make that clear. Of course, there's many ways to slice and dice these problems up, and to give a little bit of context for what we're talking about, this is one of the ways we've sliced it up, and I'll use this only to let you get some idea into the scope that we've got. It's styled on the ISO 95 process for more standard for manufacturing, and it has some overlay with mining, but it breaks down, of course, at various points. But at the lowest level, we have the mining process, the way in which the mining is done. We've defined 4 levels above that, and they're level 1, equipment control, level 2, interoperability, level 3, task execution, level 4, operation management. Equipment control inevitably rests at the sort of area of OEMs. That's their where a lot of their key IP lines. But the challenges that we see in automation are often around interoperability, and there's straightforward examples that make that clear in some of the footage that I showed earlier. We had a mining shovel interacting with a haul truck, but there's interoperability at several levels where different systems must be able to work with each other, where they must be able to flow information upwards or downwards as appropriate, and we find interoperation occurs at lots of different levels. Interoperability and task execution are the 2 areas where we've really focused our thinking so far to date and our methodology. We haven't really moved up into the operational management level, largely because in our experience that starts to cut into the way in which companies operate, and therefore they think you're becoming too invasive, particularly mining organisations, into the way they think. But that flow up between level 3 and level 4 is, of course, a very current debate. It goes under the sort of name of the IT-OT convergence in some areas. The 3 representation or 3 automation challenges that we've used to help us with our work are illustrated here in the slide. We have had a lot of experience in thinking about this problem of automating excavators, so that was an obvious one where we had a strong existing example, a lot of thinking around the way we'd solved it, and of course many thoughts on how else to address it. that particular choice was looking at the challenge around interoperability. The second challenge, autonomous trucks operating in a shared workspace. So those who are familiar with either the Komatsu or Caterpillar trucks will know that they're constrained in their ability to work with mixed fleets. So the opportunities for having both manned and unmanned vehicles, trucks or light vehicles on the same road space is limited. And so we wanted to start thinking about where things would go. And our third one, which may be the greatest challenge of all, is around the obvious need to be able to shut down equipment at quick notice. And there is the possibility that unless there's a common and agreed framework for thinking about these types of problems, that your mine super inspector or the open cut examiner or whoever it might be has to wear a Batman belt with all sorts of different shutdown mechanisms for all the different types of equipment that are out there, and clearly that's impractical. And so I think that example is quite a good one at illustrating why there's a sort of compelling need to bring things together, particularly around safety. The methodology is not one that will be too unfamiliar to many of you. It's a standard systems engineering approach to problems, but for each of those challenges we've identified a high-level use case. In the case of the truck, or shared use of workspace, we then break that down into various user subcases, and the list of these is very significant, running sometimes into tens or hundreds of examples of subcases of different things that occur in just the general likely operation of equipment in mixed fleet scenarios. For each of those sub-use cases, we look at the current workflow, the way in which they might be addressed now, or if there are several ways in which they might be addressed. We've broken that down and then posed through various fora, including a number of workshops, what alternatives might exist in an automated world if we were to change this, and we get quite significant changes in those workflows, and we get, interestingly, the same workflows re-emerging. So the idea that the automation system can replace it, but it gives us a breadth of different ways in which the problem may be solved. We then apply some techniques that are called commonality and variability analysis to try to distill out of those the key and recurring problems that form the basis for an architectural description, which we capture using a sort of pattern type language, and then distill those into architectural requirements. So I'll briefly run through an example of this, and we'll take as one of the use case for our interaction challenge, a shovel loading a truck, and the current workflow. And there are variations on this workflow, but I'll do it. At the moment, the truck backs up. He may gain some guidance from the shovel, or he may simply look to do that. The truck driver may look to back up directly. Once backed up, the shovel will load it, and when the truck's full, he'll dispatch the truck. So in this particular workflow, we've got a very shovel-centric view. Various future workflows occur. These simply repeat the existing workflow, so we're imagining an automated scenario now where the same workflow is repeated, but we get variations on this in which communication occurs here. It's a little bit difficult to read these, but the top line is what's happening on board the truck. The row underneath is what's happening. The top is on what's happening on the shovel. The row underneath is what's happening on the truck, and you can see at various points they communicate with each other, passing information. In the first instance, the truck providing any information it might have from onboard sensors about where it is, and later on providing information that might come from its onboard pressure sensors at the struts, identifying the load position. And still further variations where we might move to some type of centralised or coordinated control in which a dispatch system is engaged as well in the process. And you can build up large catalogues of these, and it's been quite good fun to run these workshops where people come together and they imagine different ways in which, at this sort of level of detail, where they're thinking about the sort of generic elements of operation, how automated scenarios may play out in the future. And from those, we bring it into this idea of the commonality and variability analysis, which looks to, it's a systematic tool which looks to pull out the things that are common and the things that are varying. And it's quite a nice and powerful tool. I won't go through the ideas in too much detail here, but you start to get some generic concepts arising, and these in turn start to raise some very well defined and cleanly articulated questions. And this is the key reason for doing this, for applying any process here. The intent here is really get to the nub of the problem. What are the key problems that must be solved if we're going to do this? Not necessarily at this point putting any giving any direction to any particular type of solution, but just trying to pull out what those architectural implications may be. And you might choose to look at one of those questions up there and have a little think about it, but each of them is quite a significant question in its own right. Continuing with that methodology, we've then tried to break it down into what are known in sort of systems engineering world, and to some extent the software engineering world, as patterns, ways of describing patterns or problems that reoccur, and methods for their solution. And we have catalogues of patterns. I'm not going to talk too much about them, but they basically, in our breakdown, they break into organisational patterns, structural patterns, and use patterns. And those organisational patterns talk about the allocation of responsibilities. The structural patterns talk about the connectedness of the system and how bits fit together. And the use patterns talk about the interactions. And of course, those patterns all connect. We have a large, significant white paper on all of this, and I'm happy to give it to anybody who is interested. We did this methodology. I'll take you back to the beginning. I said, when we started this, we were quite lost on how we were going to go about it. We have a number of perspectives on it. We'd done some maturity modelling, try to build up a maturity model as our first effort, and we found that was opening more questions than it answered. We looked at various other aspects of it. But in reflecting on the work that we'd done, we went through a standard SWOT type exercise, and a number of things become clear. If you're going to get full coverage to all possibilities, this becomes an enormously significant exercise. And we never set out to sort of own this space, simply to try to facilitate what was some fairly active discussions around the centre's membership in this regard. And so I've listed up there some of the strengths, weaknesses, opportunities and threats, and I hope that you can read them a little bit. I'll speak to one and only one of them, and that is the opportunity around establishing a common language. One of the things that, one of the good things about being in a university is you get to interact with lots of different people all the time, and you come to become familiar with their ways of thinking and the words that they use and the language that they apply. And we observed a significant gap between, in doing this work, between the various stakeholder groups who'd all come from their own methodologies. So OEMs think about the world in one way, miners think about it another. The integration guys think about another. Researchers are very good at acronyms, so we have our own language as well. And just the opportunity to find a bit of common language has been something that's been probably a really good outcome in getting people to start thinking together, and getting the mining guys to read about systems engineering, and the OEMs to read a little bit about the mining engineering world and so forth. It's quite an interesting world. Moving forward, we're going to continue with this. We've got what we call several perspectives on the project, and the next perspective, what we're going to apply, is what we call the risk-based perspective, in which we look to break the problem down and consider it from various risk points of view. So if you're a mining operation, I think that is one of the key ways in which you want to look at anything that you do, and also continue to apply to some of our familiar examples, so the dozer project and the automated excavator project. So those are all the things I had to say, and hopefully you found this an interesting introduction to some of the work we've been doing in what I think is a really important problem.
Any questions from the forum?
Thanks, Adam Gray from ADG Mining. I picked up on what you said about system engineering, and I find that very, very relevant to my area. And in particular, when you're talking about the OT and IT, the difference between the two and the convergence between the two, I'm typically finding that IT doesn't adapt any system engineering approaches whatsoever. Have you found that in your studies? While when you tend to look at development, you look towards system engineering, and quite often I find them putting things straight into a box where they think everything is a commodity. Have you put any effort into that type of study or anything like that, or any comments along those lines?
The IT guys that we've been most involved with this have been CSC, and they've, particularly the group that we've been involved with, have had strong interaction with Boeing over many years, and they're actually pretty up on that. But there's silos of engineering, and I think this is something that needs to be broken down, probably at the university level, where we're not exposing our students to some modes of thinking which really are important in bringing large projects off and all sorts of aspects.
Some more questions?
Yes.
Alberto Diaz, Barry Gold. How you see the challenges in terms of automation for underground mining, and do you have any examples on something working regarding automation for underground at the moment?
So underground is, in carving out scope, we decided to go above ground, but clearly the enormous opportunities in automation underground and in the same set of challenges. Sandvik, one of the partners in the project, at Mine Expo, released a study they've been running in parallel. So we've sort of overlapped in a number of ways, and they've been involved in this particular work in a quite intimate way, which actually follows the same methodology here and applies to underground mining applications. And I think you can get that off their website as of last week.
Any more? At the back?
Andre Gibson, Improvement Resources. I've seen many similar sorts of situations and systems that have been designed with this sort of intent. I must say not to this scale, so it's quite impressive, but more than anything, the question is around the adaptability and configuration of such a system. Has much thought been put into being able to make it so it's configurable and sustainable, for example, when things change on site?
Those are the key considerations. I mentioned before the need for... so this is a reference architecture, the idea that you can point to a way of perhaps thinking about the world and contextualising the problem that you might be solving within an agreed framework. But the ability to change management is actually one of our perspectives that we have on the project. And again, it's not fully explored, but it's a critical part of the whole problem.
I guess just a good example of it is in situations where, say for example, routes change on site, available systems. Is there any thought into that sort of area to allow the owner of such a system to actually configure and change that on the fly?
You're asking about a specific technology, and I guess I'm talking about something that's much broader than that. And so there's a bit of a mismatch in, I think, what the question you're asking and the way I can answer it. But the ability to this is the way I see technology in the future. It's the critical lever in reducing costs, and will be applied in a ruthless way by mining companies where there is a genuine advantage around it. One of the things that often breaks down around technology is its lack of maturity, and what you're talking about is a symptom of a technology that it's just not mature enough for the many and varied uses that it may find in its working life. And I think that comes down to whoever developed it. Not it's not something that can really be addressed by this.
In front, Katie.
Hi, Ross. Anthony, Newmont Mining. Look, great presentation. I guess to your first point in opening up, just around the future of automation and essentially how pervasive that might be in mining. One of the things I find time and time again is the struggle in justifying the business case behind some of these moves, and it's obviously a huge thing moving forward for a lot of mining companies to invest in this sort of stuff. Rio Tinto, great example in terms of the drive, the motivation behind that sort of thing, but for a lot of other mining companies, especially in a cost weary environment, I guess it's a real challenge for those business cases to be put up. So in the work you guys are doing, is any focus on really teasing out and identifying that business case and how that's demonstrated, or is it still early days and conceptually identifying the problems?
I think manufacturing provides a good historical example. Through the late 80s, early 90s, there was a very strong push for manufacturing to become automated, and built around the availabilities of technologies and the emergence of different ways of completing manufacturing processes. Yet, in hindsight, the benefit they found out of all of the investments that were made were not productivity benefits on the floor, but rather the information flow benefits that were facilitated by that technology. So in this diagram here, that layer between 3 and 4, and to be brutally honest, I believe the business cases are to be built around the flow of information that improves the quality of or productivity of operations, more than any of the fun stuff around having automated bits of equipment. But being in a university, I can do what I want, so I'll play with the things that
I mean that's a fundamental point in a lot of mining organisations. Obviously, that business intelligence layer, no matter how many cracks are sort of given at it, it's still not perfect. Yeah. So,
but just bringing information up from monitoring technology is a very good example. There's enormous benefit to be gained around just knowing, what dirt's moving and when it's moving, yet few are able to really build a sustained operation around those things. It'll come. I think that if I was building a business case, that's exactly where I'd be focusing my attention.
Thanks, Ross.
Opportunity for one more question. Any takers? Ross, thank you very much for your insightful discussion. Thank you.